Hello, this is Math 2270 coming to you from the College of DuPage for the summer of 2020, and the title of this lecture is Laplace Transforms Can Solve Certain Differential Equations with Variable Coefficients. As you know, differential equations with variable coefficients are difficult to solve. But in some instances, Laplace transforms can enable a solution even of these, and that is the thrust of this lesson. Now we have to lay a little bit of groundwork here, I guess. This is a fact and it's a theorem in your textbook. If f of t is a piecewise continuous function on 0 to infinity of exponential order, then the limit as s tends to infinity of capital F of s is equal to 0, and of course that is the Laplace transform of lowercase f of t. And you might have noticed when you look at your table that everything in the f of s columns are bottom heavy. The powers of s on the bottom are higher than the ones on the top, and that will make the this limit be 0. But okay, so what does this mean, exponential order? A function is f of t is said to be of exponential order alpha if there exist positive constants t and m such that the absolute value of f of t is less than or equal to m e to the alpha t for all t's sufficiently large, t bigger than some t, capital T 0. And that's pretty much what this says. A function is exponential order if it grows no faster than this for some m in alpha and sufficiently large t. And one way to check whether a function is of exponential order or not is to compute the limit, and you get this limit. If it's finite for some alpha, then it's of exponential order alpha. Otherwise, if it's infinite for every alpha, then it's not of exponential order. Now, many functions, let me say, are of exponential order, but some are not. And here's an example. F of t is equal to e to the t cubed. Now this grows crazy fast, but you see if we did check that, and it's always positive, so the absolute value doesn't matter. We calculate this limit, and we find this limit is infinity, so that's not of exponential order. Now put a pin in this because we're going to use this in a bit to help us solve a problem. And in fact, here's the first problem we're going to talk about. We want to solve this initial value problem. And it's a second order initial value problem. And you can see it does have a variable coefficient. So there is a variable in the coefficients. So let's see how we can go forward with this then. All right. Now, here is a formula that we have not used yet. This is proven in your text and we're just going to use it. But formula 30 says in your Laplace transform that if I take t to the n times f of t, for that being an integer, then that's the same thing as minus 1. This is the Laplace transform, and it's the nth derivative of this with respect to s. Now, or of s. And this derivative has to be of s because this is a function of s. Okay, so there's that formula, and that's proven by integration by parts, and it's not very hard to prove, actually. All right, so the Laplace transform then of t, and that means n is equal to 1, y prime, and we're letting y prime be this f of t, is equal to, n was 1, so that is going to be minus 1 times the derivative with respect to s of the first derivative, and the function that we're using was y prime, so that is the Laplace transform of y prime. So this thing is a consequence of 30 with f of t being y prime. But we also have another formula, which is number 35, that tells us what is the Laplace transform of y prime, and it is here, and so it is going to be s, and we've changed to y's here, but you see if we substitute in there, it will say, all right, this is negative derivative with respect to s of s times y of s, capital Y of s, minus the y at 0, but y at 0 is 0, so this is really just negative the derivative with respect to s of s, the Laplace transform of y, and that was 0. Now this is going to be the derivative with respect to x. This is the product rule, so it's going to be the first times the derivative of the second minus the derivative of the first, which is 1, times the second. So this is what the Laplace transform of this term here is. So now what we're going to do is, that was the only place where there was a variable, so we're going to take the Laplace transform of this differential equation. And so what we get then, and we've done this many times, but the second derivative is going to give you this term. And we just did a calculation, so the Laplace transform of this is going to be 3 times that. That was the identity that we just proved. Minus 6 times the Laplace transform of y is equal to 2 over s. Now, as always, you do algebra on this. And so we do algebra, and you should verify all of this algebra. But this can be written this way. This is y prime of s is equal to 3 over s minus s over 3. Y of s is equal to minus 2 over 3s squared. And you might say, wow, that's a differential equation. In fact, it is a linear first order differential equation that we learned how to solve very early in this course. With integrating factors, this is a good review for the final. So mu of s is equal to the integral of that ds. And you integrate it, and you do some simplification. That's a minus sign there. It doesn't show up very well. So you get that this is s cubed e to the minus s squared over 6. That's the integrating factor. And you remember you multiply all the way through by that, and then you integrate both sides. But if you've done it right, this is going to be an exact differential. And so when you integrate it, you're just going to get this expression. When we integrate the other side, after we multiply all the way through, we get this plus c. So we can solve for y of s. And if we solve for y of s carefully, we get y of s is this expression. Now, we don't know what c is, and so you might say, well, we haven't really solved the equation. But if there is a solution, and by the way, a solution to this is guaranteed by some of our existence theorems, then let's say, well, what if we only hunt for exponential solutions of exponential order? And that means that the limit as s goes to infinity of this transform must be 0. But the only way that can be 0, this one is already 0, but the only way this can be 0 is for c to be 0. So c is 0, and if c is 0, that means that the transform is 2 over s cubed, and I invert the transform, and that means the solution is y of t is t. Okay, here's a problem for you to try. Solve this initial value problem, and we've got 2 variable coefficients now here, and you know what to do. Let's see how you do. Okay, so now on this one, this is what we did in the first one, and that works for this term. But we're going to also apply that formula to the Laplace transform of t y double prime. And you see what we're really doing is we're letting y double prime in formula 30 be f. So that says that t, n is 1 again, f is y double prime is equal to minus 1, the derivative with respect to s, the first derivative of the Laplace transform of y double prime. But we know from formula 36 that the Laplace transform of y double prime, in fact, is equal to this. We've used that many times. So we're going to do this. But now we look at the, we look up here, and we see that y of 0 is is 2, and y prime at 0 is minus 4. But we're taking the derivatives, and so that's really just going to drop out no matter what it was. We don't care what it was. It's dropping out as long as it is a constant. So this one is 2, so we're taking the derivative of this with respect to s. So here, what we're going to do is, when we take the derivative with respect to s with this term, that's just going to be y 0. And when I take the derivative of this is going to be 0 because the derivative of a constant is 0. And this is going to be the product rule. So this is going to be 2s, that's the derivative of the first times the second. And this is going to be the first times the derivative of the second. And there's a minus sign on both of those. So we get this. And y of 0 is 2. So that means we can write this in this way. This is what we just did with L of t y double prime minus this is what we did with L of t y prime. We get that plus y of s is equal to, and I did a transform of this, and I get 2 over s. We'll solve this, and we work and we solve it, and after a while we come across with that this is y prime of s times 2 over s, y of s is equal to 2 over s squared. Make sure you can follow that logic. But this is a first order differential equation, linear first order differential equation. You should verify that this is a solution, but we find out that this, then the solution of this is y of s is this, and I invert the transform, and I get that this is 2 plus this c t. Now, the thing I haven't used yet is I haven't used this condition. This is minus now 4. More than ever, time so if I take the derivative of y, the math, it will make you substitute. And now more than ever, take care of yourself. Find out that c is minus